this morning this lecture will be quite dense, so I probably will take the entire hour, and there will be time for discussion, because there are several, let's say, information that might be useful for you, coming out from recent searches that led to the discovery of the standard model boson, or something that really looks like the standard model boson. I have to remind you that the discovery of the standard model Higgs boson was basically the highest priority goal of the machine, LHC, and the experiments, ATLAS and CMS, that were built to discover new physics in general, but in particular to solve in a way or in another this issue. The Higgs boson has been proposed to provide an elegant solution for the question of the electroweak symmetry breaking, the fact that we have an interaction whose range is infinite for the photons and very small, 10 to the minus 18 centimeter for W and Z. So there are, I would say, photons or carriers of the electroweak interactions that have such a difference in mass that something should have happened there. So the solution that was proposed by Braut, Engler, and Higgs was to imagine a field, a scalar field, occupying every corner of the universe. And this field has quite a funny potential. It's called maximum hat potential. As a value at zero, which is non-vanishing, you see here, it's not zero. And the scalar bosons appear as an excitation of the field, and if there are horizontal excitation, you have photons, massless mode. If you have vertical excitation, you give mass to this carrier of the electroweak interaction, you get to W. The only big problem is that the theory does not predict precisely the mass of the boson. So the mass of the boson is basically a free parameter. So the search for the Higgs boson was based on the fact that you have to look for something in a wide area of mass. So it was completely different from the search for the W and Z, in which there were predictions to look in a region between 80 or 90 GeV. Now the region to be searched for is between 100 GeV and 1000 GeV, so it's extremely wide. I want to remind you some of this connection that Grosjean also described you, which are very simple and elegant, connecting together the mass of the Z, the mass of the W, cos theta Weinberg, and the G Fermi. And I want also to highlight the point that once you have discovered the mass of the Higgs boson, you have discovered this boson, you know the mass, V is known, is 246 GeV. So you know lambda. Lambda is very important because it gives you the evolution of the potential of the Higgs boson. So once you have discovered Higgs, you know also how this potential will evolve with energy. And this will be an important part of the talk at the end. So what we know before LHC? We know that there is a relationship between the mass of the W and the mass of the top, which is connected to the mass of the Higgs. This green area are the regions in which the Higgs could lie, but the constraints coming from electroweak measurements, these blue ellipses and this red ellipses, the most precise are those who are coming from left and tevatron, hint that the favored region is in the low mass region. Here you see the mass of the Higgs is 114, here the mass of the Higgs is 1000, although there are logarithmic dependencies. So in principle, this is the most favored region. So everybody expected the Higgs to be found in the low mass region, but as experimentalists, we should be skeptical about our friend theorists, because sometimes they predict a certain object in a certain mass, and then we discover in a completely different region, and then they come back and tell us, yeah, you are right, we had forgotten some next leading order calculations, and you are, so we have to be careful in terms of, we have to take seriously our friend theorists. We both have to be careful, but as experimentalists I recommend also to take very seriously the recommendation by theorists, but would be a bit risky to produce an experiment which is very expensive, requiring years of effort, thousands of people, just to look in a very narrow region. And so the idea is to be able, to look particularly in this narrow region, which is the most favored one, but also to have the possibility to span, to have a reach which is much larger, because nature sometimes could have corners that should be explored and which were absolutely unexpected. I remind some of you that there was a period in which the top quark was predicted to have a mass of 40 GeV. And so most of the predictions were quite unanimously highlighting the possibility that the heaviest quark should be around 35 or 40 GeV, while we have discovered it at 172, etc. So this is right. However, in terms of detector design, basically LHC and its major detectors were conceived to explore the entire region. Although in this particular corner there was particular attention, the low mass region that is basically favored by the electroweak constraints, there was always a particular area. So let's go now through the standard model is production at LHC. You heard already something of this in the lecture by Christophe. And here you see that, for example, the main production mechanism, the gluon-gluon fusion at LHC. You see there is also a big band. This is another thing that I have to highlight. There is a big error band. The cross-section versus mass is predicted with errors which is at the level of 15–20%. And this is a thing we have to improve, because now that we have discovered the Higgs, we want to understand better the properties, and one of the things we have to do is to improve this accuracy in the production cross-section. The second most important production mechanism is the vector boson fusion. Once it is a W or a Z that fuse and produce a Higgs boson. You can see here different production mechanisms. There is another important mechanism, the associated production. We see we use this. We use basically all of this in the search. Although clearly this one is the most important one in terms of rate and in terms of, let's say, statistics. Associated production means that there is a sort of Higgs stratum from a W or from a Z, or you can have an Higgs stratum from a top quark. Basically, you radiate off a top quark Higgs boson. This is very important to establish the coupling of the Higgs to the top, but it's really very tiny cross-section. Clearly, if you take a look to the value here, if you take a look in the low mass region, 100, 120, we are talking of quite sizable cross-section, 10, 20 picobar. Remember that we are collecting femtobar of data. So again, remember the first lectures, 10 picobar, a few femtobar, so you have already thousands of objects produced. Clearly, then you have to take into account acceptance, efficiency, and you might end up with a few tens or a few handful of objects. But in this range, the production cross-section are quite simple. The width of the Higgs boson changes with mass. This is another complication. So we are looking for something that in the very low mass region is very narrow, a few MeV, much smaller than the detector resolution. So your width, the width that you measure will be dominated by the detector resolution. The natural width is really a few MeV, 3–4 MeV. But if you go high, if you go to 1 TeV, basically the width is proportional, is basically 1 TeV, so you lose the definition of particle. So again, this is another complication. We have to look in a large range of mass to a particle that is very narrow in the very low end of the range and is very wide as soon as you increase the mass. So again, this has implications in the experimental search. The things becomes even more complicated if you take a look to the decay modes versus mass, where basically I suggest you just to remember things. First of all, the theory predicts that the decoupling to the fermions goes with the square of the mass of the fermions, while the decoupling to the vector boson goes with the 4th power of the mass of the vector boson. So basically, whenever there is the possibility to have two on-shell W or Z, the Higgs decays to W and Z. So as soon as you reach this threshold, which is about 160 GeV, so twice the mass of W, the decay modes, which are the most favored one, are WW and ZZ, and only the top, which is an heavy quark, survives with some contribution. So in the intermediate and high mass region, basically the decay modes are WW, ZZ, and top. While since now you require that below 160, you require that one of the W is off-shell, is virtual, Then you have a roll coming out also from the other possible decay modes, in particular the BB. At 120 or 30, the BB decay mode dominates, is about 60% of the total branching ratio. Gluon you don't see because are jets. You're overwhelmed by too much QCD background. You can look for tau. This is possible. CC is out. You cannot distinguish the jets with the quark content of C of char. While you can have a look to gamma gamma, though the branching ratio you see is 10 to the few 10 to the -3, so it's very small. This channel is very important because you can profit of the fact that there is very small background below the signal. So basically, in the low mass region, you have all the channels apart the TT bar. You have WW, ZZ, BE, tau tau, and gamma gamma. While in the high mass region, basically concentrate the effort in WW and ZZ. This slide I like a lot because it is slides taken from our preliminary studies, our physics TDR. So before taking data, we produced a book of 1,000 pages in which we describe how well we could have done physics. And if you take a look to this book, you immediately realize that you can throw it in the basket. Because basically, as sometimes happen, so the world in Monte Carlo is completely different from reality. So it's useful that you do exercise while you prepare an experiment in trying to train the people and yourself, how can I do this search, or this search, but in terms of realistic analysis, these exercises are very often quite useless. And this is an example of this. So this is the way in which we were dreaming of discovering the Higgs boson at LHC. The idea was to use a single channel for a discovery. The machine was running at 14 TeV, so big cross-section. We were supposed to take a look, 100 inverse femtobarn of data. Take a look to this number. No? These are plots produced with 100 inverse femtobarn. The idea was that the machine would have immediately delivered in 1 or 2 years huge statistics because the machine was supposed to run at 14 TeV and 10 to the 34. This was the plan. In this condition, discovering the Higgs boson would have been relatively simple. Because take a look to this region. In the low mass region, we just use the Higgs to gamma gamma. And then you have background, but the Higgs signal becomes quite sizable. You can see by eye. And you have 5 sigma discovered there. I mean, once you feed the background, you subtract it, you have a peak, it's 5 sigma, you have discovered the standard model Higgs boson at 140 GeV, 130 GeV in this case. In the intermediate region, you use ZZ, and then again, it is relatively simple to have a nice peak, in this case at 150, for example, GeV. In the high mass region, you use again ZZ, one Z going to 2 leptons, and the other Z to increase the branching ratio going to 2 jets. And again, now the object is broader because it is a high mass object. But again, the background is really very small, and there will be no doubt that you have discovered something around 900 GeV here in this region. Again, this was the dream. And we had to abandon this dream because of the incident. I remind you what I tell you at the very beginning. LHC started with the idea of moving ahead at 14 TeV and 10 to 34, and we had to review all our plans because of the incident in 2008. So the machine would have worked at 7 TeV and luminosity would have been 10 to the 32, 10 to the 33, so factor 100 or factor 10 below the plans. And so we had completely to change all our plans. This is reality. Reality completely different from the dreams, as usually happens. In these plots, you see, those plots were produced in October 2010, so not too long ago. And at that moment, we were reviewing all our analysis. We decided to throw really in the basket the physics TDR and start from scratch the strategy, define from scratch the strategy to look for the Higgs. And here you see in these plots there are the sensitivity of CNS with 5 inverse femtobarn. Now, you shouldn't dream anymore of 100. 5 was probably something that could have been realistic. So factor 20 below. Here you see the sensitivity to exclude the standard model Higgs boson versus mass. Whenever you see data below 1, you should interpret it as an exclusion of the presence of the standard model Higgs boson in this particular mass. And here you see the projected significance of the signal, again versus mass. You see the different colors now. Now there is not anymore a single channel which is able to give you enough information to claim that you have excluded the standard model Higgs boson or you have discovered it. Now you have to put together several channels and tens of sub-channels. You see, now you have gamma-gamma, V in VB, VBF in tau-tau, WW into lepton 2. Again, all this is just a small simplified version of a more complex description in which really we had to put together literally hundreds of channels, each one providing a small piece of information. There was no single channel able to provide us enough information to claim that we have a discovery or we have an exclusion. So we had really to change completely the world. And the numbers, take a look here. If we would have been lucky to have the Higgs boson around 180, 60, 70, we could have had with 5 inverse femtobarn 6 or 7 sigma, again, putting together all these channels, doing a huge and patient work. But if it would have been hidden here in 120, 30, you shouldn't expect to have more than 2, 3 sigma. Again, everything becomes now extremely tough, because you don't have 14 TV and you don't have 100 inverse femtobarn. So real life is much harder and tougher than what was imagining at the beginning. Here you see an example of the many channels that you have to explore in the so these are the main decay modes, but each decay modes you have to consider, you have to subdivide in other sub-channels. So this is why in one of the lectures I was answering a question. We really needed hundreds of people because each sub-channel requires a small group, maybe 2 small groups, to cross-check each other, and then you end up with huge number of people needed to perform this kind of search. This was really something unprecedented. I never saw in my life a collective effort of these dimensions. If you put together CMS and Atlas, I really imagine there would be close to 2,000 people working day and night for months or years to discover the standard model Higgs boson, and at the end they succeeded. But really, it was something that was even difficult to conceive at the beginning. At the end, now we see that it has been done, but I would have been very skeptical if 2 or 3 years backward, somebody would have told me, we would put together 2,000 people and we discover the standard model Higgs boson. This was considered really something impossible. I want to highlight another point here, that with the events that you expect once you take into consideration the branching ratio and the efficiency that you have, for example, in the low mass region, 120 GeV, events that you have in WW to lepton to neutrino is about 100 with quite a sizable background. While in the very clean channel like the ZZ, you have 1 event per femtobarn, 1.5 event per femtobarn, so really a handful of events. So again, just to give an idea of the challenge. Anyway, since we were a bit crazy, we decided to really set this as a major goal. In 2010, at the end of 2010, we set up this mission impossible. We discovered the standard model Higgs boson, or exclude it forever, before entering the long shutdown, needed to run LHC at 14 TeV. No matter that we were at 7 TeV, we'll do it. And this was the crazy plan. But I think it paid off because if you're here today, and I can describe you the excitement of the discovery, is basically because, again, in a big collaboration with hundreds of students working really enthusiastically, this challenge has been taken very seriously. And they really did something that was completely unexpected. They improved everything to such a level that this, that we consider really mission impossible, actually was achieved. This is due to the fact that really we have this huge potential, this huge collaboration. Hundreds of young scientists like you can do things that in principle could be considered really impossible. We have to be confident in this. Okay, I want to give you some for people that are not really working in the LHC detector, some Higgs hunting basic, you will see some of these plots that we call Brazilian flag plots, because the colors are the colors of the Brazilian flag, green and yellow. And basically, you have to interpret this plot in this way. Whenever, take a look to one. Whenever you see a dotted line, the dotted line are the expected sensitivity. What you expect you will see versus mass. The solid line are the observed data. So those are the data. So take a look to the solid line versus the dotted line. Whenever the solid line is above the dotted line, you can talk of an excess. But excesses that are above the dotted line but below 1 are not really very significant. Because once the observed curve is below 1, you are excluding the standard model Higgs boson in this particular region. What is interesting is to take a look to the regions that in which you have an excess with respect to the dotted line, with respect to the expected rate, and the excess is above 1, which means that is an excess and it belongs to a region in which you cannot exclude the standard model. This could be the hint that something is happening. I'll explain you later on while describing some of these graphs what is that. The first breakthrough came up in 2011, at the end of 2011. And the reason of this breakthrough is very simple, because basically we had been promised by the machine people that in 2011 they would have delivered us 1 inverse femtobarn, but in practice they delivered us close to 6. So this was really the major breakthrough. So with 1 inverse femtobarn, we would not be in position to say anything on the standard model. With 5 or 6, we enter the discovery territory. Remember the plots that I showed you before. At 5, you should start seeing 2-3 sigma effect in the low mass region. And actually, we reached this position at the end of 2011, in December 2011. So for the first time, the amount of data, 5 inverse femtobarn, was large enough to say, to allow experiment to say something significant. And this is what we saw. This was the special seminar that was called in December 2011. This is Atlas results, and this is CMS results. And again, in this Brazilian flag plot, you see that basically there is nothing in the high mass region. This is 200, 300, 400, 500. In both experiments, basically the observed limits are always below 1, and there are fluctuations around the expected, but those are really what one should expect to see. And the only thing that seems to be really strange is what is happening here in the low mass region. So, for the first time in December 2011, we saw 2 experiments excluding the standard model Higgs boson in a large region. And they had a problem. You should remember that every discovery starts with a difficulty in excluding. You start excluding things. At a certain moment, you hit a wall, and you say, I cannot exclude it anymore. And sometimes the reason is that there is something there. And this was exactly the case. So we were not able to exclude below 127 or 29 because there was something happening there in the low mass region. And if you take a look you zoom in the low mass region, you see both in Atlas and CMS, there is an excess of events that quite intriguingly was clustering around 125, 26. Again, experienced physicists at that moment thought we are dead. Because once you see 2 experiments, although the statistical significance of DSS was not large enough to claim the discovery, because it is 2-3 sigma, it is exactly what we expected to see if the standard model would have been there. The fact that both experiments saw in this particular region, exactly the same region, the same excess, was hinting that something really important was happening.
Excuse me, this is a kind of all the channels.
Yeah, putting together all the channels, as I did. Yeah, no, a single channel you see 1 sigma, 2 sigma, really very small amount. But however, these 2 peaks were dominated, as it will happen also for the discovery, by the X to gamma gamma and X to ZZ, which are the 2 high resolution channels. Anyway, still the statistical significance, you see, green is 1 sigma, yellow 2 sigma, so we are really touching 2-3 sigma. It's not something that one should claim, okay, now we have discovered the standard model is boson. And we decided, since we were going to take new data, yes?
Excuse me, once again, what does it mean if a solid line is above dot line but below line?
Yes, for example, this one. This here. No, this is considered quite possible, because in principle you shouldn't expect to have the solid line to be exactly on the expected. So there will be fluctuation up and down. So in some region you will have some slight excess. We are talking of 1 sigma, for example, here. And in some region you have slight deficit. Maybe you see also. You see here, no, there are fluctuation up, fluctuation down around the expected values. And this is considered normal because, again, it's an average that you have, and statistically you might fluctuate up and down around the expected. Question?
I'm sorry. Nice question. Why it's okay to have that line below dot line? I mean, like around.
Sorry?
400.
Sorry, can you read?
Can you show previous slide?
Yeah.
Why it's okay to have observer data below the line?
Yeah, it's possible because here, for example, what you see here is a deficit with respect to expected value. But the deficit, again, consider always that we are talking of 1-2 sigma. So it is not a surprise to have, for example, in channel like for this region, the channels which are important, WW and ZZ, you might have a deficit of events in this particular region that gives you a couple of sigma fluctuations downstream. Yes?
But what I was wondering about that, if you have several points below, I mean, is it still 2 sigma? I would think if you have several points.
Yeah, it could be even more. But remember always that here in this region there are really a very small number of events. We are talking of background which is basically very, very small, but also the possible signal is very small. And so once you subtract the background, you might have easily, you might go down below 0, basically. This is what happens, this is what this curve tells you. So in the extrapolation of the background, you subtract it, and you might easily go below 0 in a particular region. So there is nothing, let's say, anomalous there. I would be surprised to see it always on top, because if you see it always on top of the expected, there is something wrong, because the statistics should be, on a large spectrum of mass, should be followed. Anyway, since December 2011, we took new data and we decided to go for blind analysis. Again, since we saw a hint of a signal, to avoid any psychological bias, we decided to look at the new data without allowing people to take a look to the signal region. So we decided to take a look to the data in the background region, to study in detail those, but nobody was allowed to perform studies or optimize cuts looking at the signal region. It would have been too dangerous, because psychologically one is, let's say, somehow tempted to enhance the sensitivity, tweaking a bit the cuts such that you have the signal going up. So we decided to do it just for safety. Both experiments did it quite well. And then we take a look to the new data. And first of all, before moving to this, I give you some hint of the expected sensitivity. Now I concentrate the attention in the low mass region. Take a look. Now we are exploring 110, 145. And these are now the expected sensitivity for different channels versus mass for a data set, which is the data set we presented in ITEP in May. 5 inverse femtobar 2011 at 7 TeV plus 5 inverse femtobar 2012 at 8 TeV. This was the data set we had. Factor 2 more with respect to the set. And here you see for the different channels, different colors, the different sensitivity. So what one should expect from different decay modes. And take a look from the purple one, X to tau tau, the sensitivity. So if there is a signal, this black curve is the if you wish, the local p-value, if you wish, the single strength that you might get if there is the standard model Higgs boson at a certain mass. Take 125. Overall, you should expect to see something between 5 and 6 sigma. This was the expectation. If there is the standard model Higgs boson, with 10 inverse femtobarn, you move from 2-3 sigma to something like 5 sigma. Okay? But how it is composed? The X to tau tau channel does not contribute much. You see the sensitivity is low. You see here is up, maybe 1 sigma. But then there are fluctuations. This is the average value that you expect. And the same is true for X to BB. The two fermionic channel does not really help you too much. You do it, you do this work, but don't expect it to discover the Higgs boson through X to tau tau, X to BB. The three channels that might contribute are the blue one, which is the X to WW, in order of sensitivity, the green one, which is X to gamma gamma, and the red one, that is X to ZZ. So the discovery, if any, would have happened in these three channels. This was the plan. Those three channels will be the key ones to see if there is something there or not. Okay. However, I will describe you also the other channels because first of all are important for future studies, and secondly, it is also quite instructive for you to have a complete picture. I don't give you all the details of the slide. You will have the slides, you will take a look eventually, but just to give a broad overview, and also give you a hint of the complexity of these studies. For example, X to tau tau. For X to tau tau, we study different production mechanisms. You might remember the slide at the beginning. Gluon-gluon fusion with the loop of top quark. In two cases, with the zero jet and with the gluon jet coming up in association with Higgs. So then the Higgs goes to tau tau. Higgs going to tau tau produced through vector boson fusion, so fusion of W and Z. Higgs going to tau tau produced as Higgs stratum from W boson. So three different production mechanisms. In addition, we study different decay modes. So the tau tau that you use to type the invention of the Higgs boson use different final states. For example, you study 4 independent channels, one tau going to electron neutrino, the other one going hadronically, another one tau going to mu neutrino, the other one going hadronically, and then 1 electron and 1 mu, and then 2 mu, and so on. If you combine everything together, you see that you have really already in this single channel many different categories. So it's not a surprise if I bring you to a meeting of the X to tau tau group and you find 30 or 40 people. They are needed because they are needed to cover all this channel. So this is the name of the group. However, what you see in data, this is an example from CMS, is not really striking. Again, remember the sensitivity is very low. Here you see, for example, in one of the most sensitive categories, which is the VBF category, here you see how it will appear a signal of Higgs boson at 125 GeV decay into tau tau. And you see, you have in yellow the Z in tau tau peak, which is irreducible background in your search, the most important one. It is a 90 GeV, and you see that basically the Higgs signal is this red component here, is a tiny signal there. So what you expect to see, if you're lucky, some excess in a couple of beams over there. Very tricky, very difficult. It's very important, you see also, if you take a look to this particular plot, you understand how critical it is. So people spend months of effort to reduce the width of the Higgs in tau tau, to improve the resolution. Because if this width is too large, there is no hope to see this possible signal. So you can try to see something. You can try to associate maybe some hint of something happening here, only if the width of this peak, which is the Z in tau tau, is small. So this is why people did a huge effort to reduce this, the resolution of the Z to tau tau as a preliminary step toward the searches for Higgs to tau tau in this region. But anyway, those are the data. 10 inverse femtobarn, frankly speaking, there is not much there. And in fact, if you take a look to the plot, you see that basically this is the expected, this is the observed. There is nothing. So if I would see X to tau tau, I would conclude I don't see anything there. However, the sensitivity is small, so I'm not surprised. X2BB, another very difficult challenge. X2BB, you cannot look at X2BB in directly, because there is a QCD background, dijet background, QCD going to digest pure BB digets, that is really overwhelming, orders of order of magnitude on top of your signal, so no hope about it. So the thing we can do at LHC, and actually it works quite well, in this particular case, we study associated production. So we ask for an Higgs boson, decay to BB, produced in association with a W or with a Z. In addition, to enhance the signal, the capability of some signal, we ask the Z or the B to be highly boosted. Again, we want to have a clear topology to be studied. For example, in this particular case, we ask for the PT of the vector boson to be 160 GeV. So these are typical events you see, for example. In this particular case, we look for Z produced in association with the Higgs boson, decay to BB, and you see Z going to invisible. So we have large missing ET here, and there, recoiling against the Z, two highly boosted B jets, which clearly becomes very, very close by. And then these B jets should be B tagged. So you apply B tagging, and so you are getting rid of the most important background components. However, is another very tough channel. Again, putting together different decay mode, different vector boson mode, different kinematic condition. At the end of the day, you end up with plots like this, in which this is a multivariate analysis, a boosted decision tree variable that is used to enhance the sensitivity. But you see, even, I mean, really doing your best effort, you see the signal will be this small red excess on top. This is logarithmic scale, so it's really tiny signal you might see. And in fact, here you see again, maybe some positive fluctuation, but nothing really significant. So again, these two channels, to summarize, tau tau and BB, at least with statistics of 10 inverse Vemto, but they don't tell us much in terms of presence or not presence of the standard model. This is the one that starts telling us something. And so it's one channel whose sensitivity is large enough to start telling us something. X to WW, with both W decaying electron. Again, same story. We study different production mechanisms, gluon. In addition, zero jet or plus jet sample. In addition, VBF. Again, 6 categories, many subchannels, same story as before. Here you have a signal purity, signal to noise, which starts to be reasonable, 10%. It's not great, but we can work on it. 10%, 10 signal, 100 background. And this is the typical event that you see, in which you have basically two leptons, each one coming from a W, missing ET because you have a neutrino, and the typical feature that would distinguish these kind of events from the irreducible WW background. You remember that we studied at length the diboson production exactly because this is an irreducible background of this channel. Is this one. For example, the angle, the opening angle between the two leptons should be small, because if those two leptons are produced by WW decay products of the Higgs, the two leptons are emitted in the same direction, while if they are produced by WW as a non-resonant background, those are produced at larger angle. So what you do, basically, you study events, WW events, in which the opening angle between the two leptons are quite small, or if you wish, the transverse mass of the system of the two leptons is very small, because again, we are looking for another state. And here you see, for example, in the transverse mass or in the invariant mass of the two leptons, this is CMS and Atlas results, again presented in Ancher. And you see that now the red curve due to the signal is a bit more visible in expected data. And the data again, in the region in which you expect some excess, it appears to be that there is some excess in observed data. But again, this starts to be a bit more convincing than the previous plots, but still is not enough to claim that we've discovered the standard model is boson, because the presence of the neutrino does not give you a clear peak. It's a broad excess. You have neutrino in these events, and so you are not able to reconstruct the mass of the Higgs boson properly, and so you have correctly a broad excess of events in the region in which you expect to see the signal. You should expect to see it if the standard model is boson is there, but you cannot use this to claim we've got it. So it is too, nobody will believe you that we've discovered the standard model is boson based on these two plots. Okay? Although it was very important to see them, because those were the first hint that really something was happening there. If you would not have seen them, then would have been worried, because this channel is sensible enough that if the standard model is there, you should see some excess. But again, the excess is not significant enough and not narrow enough to claim that you have discovered new state of matter. And this was done by the other two channels, which are the X to gamma gamma and X to ZZ. Those are the two channels that really produce the discovery. X to gamma gamma are very simple events, basically two isolated photons, high PT photons. It's important to have the best possible resolution of the calorimetry, because we're looking for a tiny signal over a smoothly falling ground. The resolution that you have typically 1–2%. The signal purity depends on the categories you have, but typically is from 3 to 30%. So clearly you see that now we are moving toward higher and higher signal purity, and mostly higher and higher resolution. High resolution means that you might now see a peak. And this is a completely different scenario with respect to the previous studies. Again, X to gamma gamma, we study different production mechanisms, gluon fusion, BBF. We subdivide again the sample in different categories of different sensitivity, and you might start seeing something again. I don't know if you can see that in different categories, even by eye, you can see that there is something happening around 125, but you can see really much better when you put things together. And these are the results of the different categories put together by Atlas and CMS. And clearly now you see a clear peak visible around 125 in both experiments. And the statistical significance is between 3 and 4 sigma. So now we start thinking that really there is something happening in this region. It's compatible with the fact that we see an excess in WW, and it's now both experiments, they see in the same region a peak. So now we start believing that there is something happening in this region. And the issue was closed by the last channel, which is called actually the golden channel, which is X to ZZ. Events are very simple. Basically, in this case, you have 4 muons, each one coming up from a Z. One Z is on shell, the other one is off shell. And this is an extremely clean signal. Basically, the signal to noise is 1. You have 1 signal, 1 background, roughly speaking. So, extremely clean. However, statistics is very poor. You shouldn't expect to have hundreds of signals. You have a handful of signals, 5, 10 signal events, because the rate is very. But still, the resolution is very high, because you remember that at the beginning, we decided to have a huge, to put a huge effort in having the best possible resolution for electrons or for muons at 100 GeV. So now we take profit of it. Now we have the possibility to have 1–2% resolution at 100 GeV. So we can see again a peak, because we have a resolution of 1 GeV, let's say, over command. And this is what the 2 experiments observe. This is a rare electroweak process in which a Z goes to 4 muons through the emission of a virtual Z or gamma star. That we use for calibration. We know that this peak is 91.2, so we have a clear understanding of the absolute momentum scale. And then you see that in 2 experiments in the same region, around 125, you have a peak building up. Again, it's not striking, it's 3 sigma, but clearly now, once you put together everything, you are not surprised to see that both experiments have reached something exceeding 5 sigma. And this is the moment in which we have announced the discovery. I want to highlight a point. You take a look to this particular plot. You see, the blue one is 2011, 7 TeV, and the red one is 2012, 8 TeV. It's very important to check that the two data samples are consistent. So we saw something in 2011, 7 TeV, an excess at the level of 3 sigma in this region. We see something 3.5 sigma, maybe 4 in the same region. And so we put everything together. So the picture we got is really consistent. Atlas was the same, exactly the same. So at that moment we decided to release the prudence and to say, okay, now we can go out and say that we have discovered a new particle at the ellipse. We measured the mass measured by the two experiments. The mass is measured by the high resolution channels, ZZ and gamma gamma. And you have different measurement depending on the channel, but basically at the end you end up with the two values of the mass between 125 and 126, which are quite consistent internally and each other. And for me, it's amazing this plot, because you have to imagine, I work as many other people 20 years to achieve these results, and really you pass through moments in which you really think there is no hope. There will be another generation of physicists looking for the star, but then maybe when something appears to be completely unlikely, in 7 months, which is a very short period, everything changed. So this was December, this was February, this is July. So in a very short amount of time, immediately after 20 years of incredible effort, your life basically changes. So it was really, it's not a lesson for you. If you have a dream, if you have a goal, insist, continue, be resilient in following it, because sooner or later you might be rewarded. I want to note the fact that the energy, this discovery has arrived with the Iranian 780 TeV, which is 1/2 of the design energy, with 10 inverse femtobarn, which is 1/10 and 1/3 of the minimal amount considered necessary to discover. So this is really the result of the work that was done by these hundreds and hundreds of young people that worked so nicely to discover. Now I go the last 15 minutes. I would like to discuss with you the implications of this discovery, because now, as it happens often in our field, we have found a solution to a certain problem, but the question marks that we have now are probably higher. We have another series of questions that I would like to address, and you will be probably part of the effort to solve some of them in the next years. First of all, we have to understand if it is really the standard model Higgs, or we see already deviations from the standard model, and then we would like to understand what are the implications for the search for new physics. In some sense, there is a new field which has been opened. Now we have a new particle, extremely sensitive to the coupling to any other state of matter, the matter that we know, and also the matter that we have not yet discovered, should be aware of. So if you measure very precisely this new state of matter, you might, on one hand, check that it is really acting following the prescription of the standard model, but you might check that if there is an anomaly, this could be a hint of something new happening. So this field of precision measurement of the Higgs properties could be a laboratory to discover new physics. So it's something which is really very, very serious. And actually there are plans also to produce special machines to do the studies with high precision, like a linear fluid. For the moment, if I put together all the couplings, the decay modes, you see, and I average everything, the signal strength in both experiments is basically compatible with 1. So John Ellis concluded it works like a duck, it works like a duck. So you can draw yourself a conclusion. It really looks like the standard model. I want to highlight, however, 2 things. And this was at the time of the Melbourne, of the ITEP conference. That you see, BB and tau tau in both experiments are low. If they are low because the sensitivity is low, or they are low because something wrong is happening, the Yukawa coupling, the fermions, we don't know. So this was one of the doubts we had. Another doubt, we see a slight indication of an excess in Higgs to gamma gamma. In both experiments, you see, it is 1.5 sigma, maybe 2, above expectation. There is a bit more signal strength in Higgs to gamma gamma than expected. again, these were considered since the very beginning intriguing hints that something else could happen. So we have to take a look to it, and I will tell you in the next of the presentation the progress in this area. First of all, we have collected new data. So the ITEP results were presented in this region at this moment, and now we have 23 inverse femtones. So we are continuing analyzing the data, and we have new results coming out, and I would like to show some of them to you today. For example, results shown in November by Atos and CMS, we have clearly the first message: the signal is gaining strength, so there is no doubt that this is new state of matter, and it is increasing the statistical significance, no surprise. Here you see, for example, now the peak in ZZ, which is more visible in CMS, now it is 4.6 sigma, so it is really growing as it should be. This is Atlas shown in the CERN Council. The local significance of the X to gamma gamma only is 6 sigma, so you have a single channel in which really you see now the full observation. So no surprise there. If you put together the combination, this is the combination that was presented by CMS in Kyoto in November. Now in ITEP we were at 5 sigma, and now we touch 7, 6.9, and up 7 for Atlas. So again, this is not exciting too much. Clearly, if it is real, you will see it growing up with statistics. So nothing new. This is actually is quite interesting, because you remember that in X to BB and X to tau tau we saw nothing. Still, the situation is quite complex, but those are recent results from CMS, particularly on the coupling to fermions, because you should realize that if the coupling to fermions does not work, clearly this is difficult to claim that this is the standard model boson. So if it is the standard model boson, it should be coupled to W and Z, custodial symmetry, but that should be also coupled to fermions, otherwise it does not, somebody else should give mass to the fermions. So it is quite an important subject, although it is very difficult to establish because the coupling, the sensitivity of this channel is quite bad. However, you see that now with 5 plus 12, you see with additional statistics, one starts seeing something. Take a look to this plot, which is the invariant mass of the BB bar system. Remember that the BB bar is produced in association with the vector boson, with the Z or with the W. So what you see in green is another vector boson, which is the major background to this search, so 2W, 2Z. But then you see in the region in which you might have something coming from the Higgs boson at 125, so a bit away from the 90 GeV peak, you see that there is some hint of something happening. I'm pretty sure that with additional statistics this could become a reasonable peak. Anyway, I would say that today, if you translate this in excess, we see a 2 sigma excess in X to BB, and these are the equivalent plot for X to tau tau, in which you see now that there is a broad excess, as one would expect, still low, level 1 sigma. But again, recent indications are that the coupling to fermions is not wrong. There is something happening there. We didn't see it yet because the statistics was low, the sensitivity was low. I expect that with full statistics, this issue will be over. There will be no further questions that the U-gamma coupling is at work. This is at least my expectation. So again, if you wish, if you put together everything, you put together the coupling to vector fermions, the coupling to vector boson, here is what you would expect to see, standard model, 1, 1, and here is where we are. It is within 1 sigma from. So we can conclude this, it continues to work like that. So really, it is really the consistency with the hypothesis that it is the standard model boson is gaining some strength. Still, we have to conclude, we have to establish if we have really observed the scalar, because standard model boson is a scalar, and many studies are ongoing to try to solve this question. The way in which we address this question is a traditional way that was used from the pi0 time. Basically, we look at the angular distribution of the final decay products, because this angular distribution contains the information on spin and parity basically of the state. And there are three approaches that we are using. We use the decay to two photons. If it is spin 0, it should be flat in cos theta star. If it is spin 2, it should be quartic in cos theta star. So we try to use this as discriminating variable to understand if we can assign some certain probability to a hypothesis. We use the x to gamma to zz for leptons. In this case, the information is contained in the angular separation between the planes of the decay products, which contains information on the hypothesis scalar or pseudo-scalar. And we use also the x to WW in two lepton to neutrino. You see here a simulation of a polar angle distribution for a spin 2 particle, which is clearly diagonal with respect to the information of a spin 0 particle. So we use all these three information to put together, let's say, to check the hypothesis if it is effectively 0 plus. And here is where we are. This is really fresh results produced by Atlas and CMS. Still, the separation is not huge. Take, for example, CMS results. These are the data. This is the hypothesis 0 plus. This is the hypothesis 0 minus. There is some tension. This is fully consistent with 0 plus. So, quantum numbers predicted by the standard model. But still, there is 2.4 sigma away from the hypothesis 0 minus. So we should be weighting it. With additional statistics, this separation will increase. This is the same for Atlas. Again, fully compatible with 0 plus, some tension with 0 minus. Atlas, again, these are the data, fully compatible with spin 0, some tension with spin 2, but too early to conclude. But I would be surprised if in Morion, for example, within a few weeks, this issue will be still on. Very likely, we'll conclude soon, in a few months, with the statement, we really do see a scalar with parity plus. So, but anyway, the current status is basically we are looking at something that really looks like the standard model Higgs boson. So the question, the last 5 minutes I want to address, then we have a problem, because again, we know that the standard model does not account for some important phenomena, like dark matter, dark energy, inflation, does not incorporate gravity, neutrino masses and hierarchy are out. So there are a long list of mysteries or unknown that are not described by the standard model, the definition of the standard model. So we have to understand if there is physics beyond the standard model, but in particular at which energy scale, because now that we have measured the mass of the Higgs, now we know also the evolution of the Higgs potential. And if you take a look to this plot, which has been produced quickly by the GFIT group, in which you have the mass of the W and the mass of the top, and now you have the mass of the Higgs in this region, you see that everything seems to be very consistent with the standard model, being the only explanation of matter and nature that we have. So if new physics does exist, it appears to be weakly coupled at weak scale. So we have to be, it's a new challenge. It should exist because it should explain things that we don't understand. But it is not easy to understand where it is. We have to work on it. And in particular, I like this because basically we have understood everything up to here, 100 GeV. And we would like to go there, to go up to the Planck scale. And in this gap, there is something to be really understood. Today we know that with the mass of the Higgs, the Higgs potential might be vanishing up to the Max Planck or just before, might reach the Max Planck. This is a new thing that is absolutely new since the discovery. And now that we know m, we know lambda. And so we can compute the evolution of the Higgs potential. And to our surprise, the evolution is compatible to reach the close to the Planck scale. But again, you see here, there is a strong dependence of the mass of the top, for example. Here you see 10 to the 10, 12, 14 GeV. And so a small difference in the mass of the top might change completely the picture. This is why yesterday I was telling you we need to measure well the mass of the top, much better than 1 GeV, which is the current precision, because this has an implication in this kind of evolution. And again, it is possible that the standard model runs up to the Planck scale, but it will be severely constrained by the need that the couplings of the new boson are really exactly the one predicted by the standard model. This is why it's so important to measure the coupling, to measure them very well. And the ideal world will be to measure them at the level of 1% accuracy, to be able to spot a few percent anomaly that would hint at the presence of massive particle entering into the Higgs. Another thing which is intriguing is this diagram, in which you can put the diagram of state of the electroweak vacuum, which could be considered the diagram of state of our universe, which depends, again, with some heavy assumption, I would say, on the mass of the top and the mass of the Higgs. And now that we have the Higgs here, and we know the mass of the top in this region, it's quite amazing to see that our universe appears to be in a metastable position between full instability and full stability, which is, again, quite intriguing, because it could hint that there is something behind this. Again, there are heavy assumptions producing this plot, but it's another hint of the need of measuring well both the mass of the Higgs and both the mass of the top to have a better understanding of this contour and to have a better understanding of these scales, 10 to the 10, 10 to the 12, in which eventually the standard model could break. So we could have additional information coming out from this. Not to say that if mass of the Higgs will be higher than the mass needed to guarantee the stability, the Higgs could serve also as an inflator. This I think I discovered recently. Again, there are several discussions on top, but with the inflation can be produced by a negative pressure vacuum energy density, which in turn can be produced by slowly rolling scalar field. A scalar field like this could be responsible in this region for the inflation. Then you take a look to the Higgs potential, is a scalar field, and the Higgs potential, you see here, on a larger scale, there are two dips. This is where we are today, but close to the Planck scale, there is another local minimum. That if you expand this region, you see the local minimum is possible if the mass of the Higgs is exactly where we found it. It's quite intriguing. Some of these works were produced before the discovery of Higgs boson at 125-26. And it's amazing for me to discover in the last few months that this scalar with this mass could play a role in the inflation mechanism. Again, several assumptions, several constraints, but it's really another area of research. I must close. There are implications on SUSY. Yesterday we discussed the direct limits on SUSY. The mass of the Higgs boson is a strong constraint on SUSY because SUSY would prefer a light Higgs boson, but what we have discovered is a bit too heavy, too massive. Here you see an example of this. Here you see the maximum Higgs masses different SUSY models accept. And you see that in this region, you are able already to exclude or to constrain several SUSY models, while there are a few others that still survive. Again, now we have an additional constraint on SUSY. Each SUSY model should be compatible with the Higgs boson that looks like the standard model of boson at 125, which is tough, which puts additional constraint on the parameters that you have to tune for SUSY. So I conclude that basically all these studies on Higgs coupling, Higgs properties, or direct searches for new physics will continue after the repair of the splices that will happen in this year and the next year. We are going to get something like 300 inverse femtobarn of data in the next 10 years, so a factor 10 in statistics, and very likely another factor 10 in the following 10 years. So the idea will be really to use all the statistics to improve our understanding of the Higgs boson properties such that this could be a clue for new physics. I want to conclude with this plot that is a nice plot that describes you what we have explored so far. So this tiny piece of the pie is the region of phase space that we have explored so far at NHC, producing an historical discovery. We are very happy, but don't forget that we have to explore the entire pie before concluding something significant in the presence of new physics. So the recommendation is stay tuned. If you wish, participate to this effort. It will be still very exciting. Thank you very much.
Thank you very much. Questions? Sorry, maybe I missed that, but are there any efforts to see the Higgs decay to new plus mu minus, despite the fact that the cross section is extremely small?
Yeah. There are works ongoing already now. Although with the statistic we have, sensitivity is very small. But clearly this is a very rare decay that we have to establish. And with 300 in the spectrum, I'm pretty sure it will be accessible. But already now, for example in CMS, there are preliminary studies to tune all the possible tools, to optimize them, to be able to increase at the best sensitivity of this chart. It's absolutely remarkable.
These results in dB bar, are they compatible with Tevatron when they can do it?
No, Tevatron is too large, too high. But at least it was too high, to be correct. It was 2.5 times the standard model expectation, but then they corrected and they reduced. So probably now they are compatible. They were not compatible with the results published in August or announced just close to the seminar. But if I take a look to the latest results in which they have reduced the p-value of their evidence, actually now it is 2.5 sigma, while previously it was 3 point something. I think they are more compatible.
In decay mode, Z to 4 leptons, do you see real Z, or it's just 2 virtual Z?
No, it's one real Z and one virtual.
So the mass
we also accept sometimes 2 virtual Z, but if you take there is a hypothesis that I don't have with me, you expect most of the cases to have one real Z and one virtual with a small contamination of 2 virtual Z. And we do see it.
My question is about the plans outwork after shutdown. You surely will improve the precision of existing measurement, and my question is, do you plan measure something new to do some new analysis?
Absolutely. The idea is we have to be aware that this was really done in a rush under heavy pressure, and there are still room for optimization in many analyses. An example of the X to mu is one, but there are, for example, another channel which is under study is the decay mode in Z gamma, because there are models in which this decay mode is announced. In addition, I must tell you that, for example, if I go back, so we have somehow to redo from scratch everything. Let's try to go back to the really, because so far we have embedded in the analysis the hypothesis that we are looking for the standard model Higgs boson, with the cross-section of the standard model Higgs boson, the width, and the decay modes. But take a look, for example, to the high mass region here, on which I have not spent too much time. Now, what we have done, we have excluded the presence of the standard model Higgs boson in this region. But we have not, and we cannot exclude the presence of another object that has a cross-section which is 10% or 5% of the standard model Higgs boson, different width and different decay modes. That could still be there. So what we are supposed to do now, in the next year and a half before entering the new data decay, is to redo the analysis from scratch, removing the hypothesis that you are looking exactly for the standard model Higgs boson, because the fact that we have discovered one here does not mean that there is nothing else. One is, there is still room for an object which is 10% the cross-section of the standard model and acts 10% in giving the mass to the particle. It could be a companion. So we have to do it again from scratch. This is why it will be quite an important effort to conclude that there is the standard model Higgs boson and there is nothing else. And this is an important statement. Because there are many theories, supersymmetry is one, predicting that there are brothers and sisters of this statement.
Thank you.
Are there more questions?
For the machine, you mentioned here only 13 TV, not 13.
Yeah, they will start at 13, I'm pretty sure, because they will be prudent, so they will start at 13 and they will move to 14 after a few years. So at the beginning, I think we should consider 13 TV as a baseline scenario, and then as we have moved from 7 to 8, I imagine that after 1 year or 2 years of experience, if the safety system works and there are no major issues, they will move to 14. To move to 14, since the very beginning, there is a concern that there is a part of the magnets, particularly produced by one producer, which appears to be have lost the training. So it's something that is worrying a bit the experts, and they don't want to put in the magnets the full energy, the full current, because they are afraid that this could imply hundreds of quenches in the magnet to train them again. So you could lose a huge amount of time in trying to reach, let's say, 12,000 ampere, while staying at 10,000 ampere probably is much quicker. This will be the idea. But after a few years, they will try. I'm pretty sure they will try.
The velocity will be this around 10 to 23 or
In terms of luminosity, in terms of instantaneous luminosity, I think people should be prepared to something exceeding the nominal values since the very beginning. I'm pretty sure in 2015 will be beyond 10 to 24. And this machine, for the parameters, the first lecture I alluded quickly to this, but the parameters that this machine, we are measuring this machine, allows this machine to go beyond 5, 10 to the 34, and maybe higher. So this will be very, very challenging. Hey, this is an item for experimenters.
So was a question?
Can you tell us a bit about the next generation of accelerators that will be after LHC, maybe in parallel with LHC? Is there any solid plans for now, like for linear colliders?
It's not solid, but there are plans. It's not solid because it's not yet approved, financed in March, but there are serious plans to build a linear collider in Japan, very likely. However, there is an international community which is behind this, and the effort to build a machine that could be initially running at 250 GeV and maybe later on moving to 400 GeV to have the possibility to produce pairs of Higgs and eventually pairs of tops, because measuring also the top properties is very important, are quite high. Clearly the scientific community is at work. There is a recommendation of the European Strategy Group which is coming out, which strongly recommends to move into this direction. Unfortunately, the economical situation is quite tough, and so we don't know if the chance of this machine being approved are high or not, we'll see. But this will be known in the next 1.5 years. And if it will be approved, so the effort is very serious, if it will be approved, you could have this new machine in, I think, in 2025. So I imagine the ideal world will be to have two machines in competition. For example, what we cannot do at LHC, we cannot measure, for example, the invisible width of the Higgs. The Higgs could contain information on dark matter, for example. If a part of the Higgs is invisible, you could have direct limits on the presence of invisible objects. At LHC, we cannot do it. A machine in which you can scan a bit the energy, you could have really a measurement of the natural width of the boson. You can look for the self-coupling. We will try also to do it. It will be very tough. So there are complementarity between the two. And clearly the goal for both will be to reach 1% precision in the couplings to be eventually able to discover indirectly new physics. Only after this period, I think, we might be in condition to understand if it will be worth to build another proton-proton collider. Now this really comes for something in the next 40 years maybe. But if at LHC and in this linear collider, we will conclude that there is new physics, I don't know, at 50 or 60 TeV, so we will accumulate enough evidence, anomalies, rare decays, hinting that it is an interesting region, we could still have the technology to build the 80-kilometer proton-proton collider or 100-kilometer collider. This is possible, technically possible. Today we don't have the physics motivation. So if, even if I would have the money, I would not be able to explain the physics motivation, because I don't know if the new physics scale is at 50 TeV or at 300. And it is too large effort to risk if you are not sure that in this area there is something really solid.
I have two questions. First is you want to increase the luminosity, but is the electronic prepared for it? It's possible to store the data, because I know the fact about the LHCb, the electronic is not prepared to have such a huge luminosity. So in the next slide you will see that the luminosity in LHCb is to order smaller than the Atlas and CMS. So you want to say something about this?
You're absolutely right, but I know that also in LHCb there are efforts for the upgrade, the readout system. I think it is feasible for LHCb.
Yes, it will be done.
It will be done and should be done, because clearly the capability of the experiment are huge, and today they're limited by statistics, by the fact that LHCb cannot take the full luminosity that we take because of the readout, the limitation of the readout. Similar limitations would apply to us, not mostly in the readout, but I would say the trigger level.
Because in LHCb, if they increase the luminosity, they have to increase the threshold of the trigger. So
but
they haven't got more events.
This is why we should be more clever. I think as of today, we have still room for improvement in the trigger level. The trigger systems are still quite naive. I think deploying new ideas and new techniques that are today available will be possible to have at the trigger level a part of the offline analysis already, a part of the offline selection. I think it's still possible. I mean, again, if I take it to the next 10 years, and this will be true for LHCb and also for Atlas and CMS. For example, the tracking systems are not part of level 1. And if you want to have a highly pure sample of enriched Higgs going to BB, for example, I would imagine, or Higgs to tau tau, to do something in which you request the bit tagging request, not offline, but at the level of the level 1. This clearly creates a completely new approach and requires a new readout system, for example, for the pixel, or for part of the tracker. But in the next 10 years, the detectors at LHC will be heavily upgraded. And this is an area in which I think will be worth to spend some new ideas.
Okay, the second question is connected to the last conference about the strategy in the particle physics that it be held by my faculty, so I got the opportunity to take part as a technical crew. So you discussed about the many few facilities in the physics, and maybe I missed something, but you won't tell about the money. So, we know that in the European Union there is a big crisis, and what you have to, maybe you want to tell about when you have found the money to spend this.
This is a too direct question, but I can comment something on the money. The cost, for example, of a linear collider that would reach 400 GeV center of mass collision is estimated as of today 8 billions, call it dollars or francs or even euro, and there is some different, but not terribly large. Call it 8 billions euros. The cost of a facility at 250 will be something like 5 or 6 billions, because there is an entry ticket for infrastructure for that. Japan, for what I know, would be happy to provide 1/2 of the cost of the total facility. So something like 4 billions. But 4 billions is not enough to build a 250 machine. They would need 2 or 3 billions from other regions, from the United States, from Europe, maybe from China, India, etc. So these are the discussions ongoing. So we are not talking of a huge amount of money in absolute, because we might, in Europe, for example, we might be able to provide $1 billion as in-kind contribution for the cavities, for example. A large cost of this infrastructure is the cavities. And European industries can produce the cavities that are needed to build this machine. So we could have an ad hoc, let's say, investment promoted by the European community that will allow industries in Germany, in France, in Italy, UK, to work and give in kind as a contribution to the. So there are possibilities. So the money needed is huge, but Japan is really pushing very hard to have this machine. And so a large fraction of the money could be eventually secured by Japan, which is trying to use this money as a stimulus for the economy. So it's a completely different attitude in the Far East with respect to what we see in Europe and Russia and also in the United States. So I'm a bit optimistic about it. But again, since nobody knows what will happen tomorrow in the economy, it could happen that the situation could become even worse with respect to today. So all these plans could be jeopardized in a moment.
More questions?
Sorry?
Is it safe to build something in Japan?
The earthquakes? Yeah, it's a good question, because I talked with Lynn Evans, which is the project manager of this International Linear Collider. The fact that Lynn Evans has been appointed is a sign that things are becoming serious. And clearly there is an issue not only on major earthquakes, because this could happen any moment, but major earthquakes could produce a damage that would imply, for example, in J Park, if you go now today, as I was there in November, you still see part of the facility in which the floor fell down 1 meter due to the Fukushima earthquake. In this case, you stop the facility for maybe 6 months or for a year, and then you repair it. So the damage is in time. What could be damaging probably more, a machine whose beams are at the level of nanometers. So in LHC, we have beams at the level of 30 micron. You have to align these proton beams at the level of a few micron to be able to have the maximum intensity. For a linear collider, the beams are at the level of order of nanometers, and so what could be critical are not the big earthquakes, but the very frequent, very small earthquakes that could create perturbation in the normal operation. And they are studies this effect, if there are protection or I don't know, no idea. But I was myself a bit worried about this. Okay,
back to this financial situation. Maybe you think about divide the cost of the government into the private companies that you over. Have you ever think about it?
Yeah, if there is good political will, there are several solutions that are possible. Today, if I want to be frank, I see completely different attitude from countries in the Far East, China, Japan, Korea, just to give some name, but also India, in which they really want to invest in science, in basic infrastructure, in basic science. And countries in which the tradition was much stronger, like the United States, Russia, and also Europe, in which there is hesitation. There are many problems, but there is not a clear, let's say, decision to use resources to invest in science as a solution for the crisis. So this difference of attitude is still on, and is a bit risky, because clearly if they would decide in a decision similar to what is done in the Far East countries, the technical solution could be many. They could even use this part of this money to promote the economy in high technology activities, which are typical of these issues.
Okay, I have two more mostly more questions. Let us thank speaker Yu for the whole set of very interesting,